We'll have a test coming up in about 2 weeks. So definitely time to start thinking about studying for it. If you are in freshman seminar, you've been talking about different metacognition methods, and one of them is having short, very focused study sessions where you think about a specific topic. So the front side of this gives you topics that are going to be on the exam, and so you can look at, do I know how to balance equations? And if that's something that you're struggling with, maybe that can be your focused subject. If you already know that, do something else. On the back are ideas of what you can do during study sessions. A lot of what we're doing right now is the math of problem solving. And really the best thing for that is just to work a lot of problems. But there's some suggestions of things you can do. And important is figuring out why you're struggling with it. Is it the math itself? Is it the units? Is it figuring out what the question is asking? And then there's some ideas there. If you're more worried about vocabulary or concepts, you study that in a different way. So a few suggestions there. I'm not an expert on all things metacognitive, but this is the ideas of how I would start with studying. So that is for you. We are going to look at that third problem on stoichiometry paper. And I spilled coffee all over the place in the last class, so I'm gonna have to look around for it, see what I did with it. All right, so hopefully you took a little bit of a look at this because I'm going to go through it pretty quickly. Of course, the first thing we want to do is balance the equation. Anybody have thoughts on balancing this guy? On which one, the water or the lithium? Water. The water? Okay, so I half agree. I definitely want the 2 there. I would have put the 2 here. Maybe I just didn't hear you right because the fan's running and I'm struggling with that. So I would have done it like this. We have 1 sulfate here and 1 sulfate here. So I would keep those together as a group and not separate out those oxygens. This has 2 lithiums, so I would put a 2 over here to make the lithiums equal. And then I count up how many hydrogens and oxygens I have left over, and then that tells me I need 2 waters. Okay. All right, so the next thing that we want to do is decide which is our known and which is our unknown. So I'm going to go ahead and put this concentration under here. Reminding myself that capital M means moles per liter. And then I also have a volume for the lithium hydroxide, 28.41, and a volume for the sulfuric acid. Now we know we want to start with an amount, and a volume is an amount. Yes?
Well, why don't we start at just 2 and 2 with those?
Well, if I count up, on this side I've got 2 hydrogens, and I've got 2 times 1 is 2 hydrogens, so that's 4, and then over here, you got it, okay. All right, so I have 2 volumes, 2 amounts. So when I decide which one is my known, I'm looking at what do I know more about. I know more about this one, so that's my known. I'm going to call that A. And then the one I know less about, I'm going to call B. And if I look at where the question is, what is the concentration? It's going to this chemical. What's the name of this chemical? It's an acid. Sulfuric acid. So that's one of those 3 acids you need to know. Okay. So I'm going to start with the volume of my known, the amount of my known. And I'm going to do that in red. 8.41 milliliters. And I want to get to moles. So that means I'm going to have to go through molarity. And I'm also going to have to change from milliliters to liters. So I can go to this sheet here. Make sure that I have my slider on solutions, and it tells me I'm multiplying with molarity on top and 1,000 milliliters on bottom. Okay, so I'm gonna put that here. The molarity is this 0.09. And then my 1,000 is milliliters per liter. So that way my liters cancel out. My milliliters are gonna cancel, and I really ought to be writing my chemical as well, so I keep track. So this is the lithium hydroxide. So now I have, when I multiply this, moles of lithium hydroxide. And I have to throw away the paper that I had the answer on. See if this calculator works. This also got house. So anybody come up with a number for that? Yeah.
Question.
Yes.
When we have the milliliters, is it okay if we just like turn them into liters, separate from this?
Yes. Yeah, so if you wanted to start with 0.02841 liters and just multiply, that's fine. I know what you're doing. All right, so I get 0.00202692. Anybody else get that? Okay. And then I'm gonna keep my units and my chemical. That was step one. Then I go on to step two. Step two is my mole to mole conversion. So according to this, B, my unknown goes on top, A, my known goes on bottom. I'm gonna start with the answer to step one. Running out of room. And then speech again. And I'm gonna go to the sulfuric acid. Where am I gonna get these numbers? Coefficients on the balanced equation. So the sulfuric acid doesn't have a coefficient, that's that invisible one. And the lithium has a 2. So what this chemical equation says is I need twice as much of lithium hydroxide as sulfuric acid. So if I already know how much lithium hydroxide I have, I know that's twice as much as I need. So I'm going to divide it by 2, 1/2, in order to figure out how much sulfuric acid there is. So I multiply that, and I get 0.001346. And here you want to be careful about your canceling. So I've got moles of lithium hydroxide and moles of sulfuric acid. Those two don't cancel each other out because they are different chemicals. Okay, so I'm going to cross out lithium hydroxide with moles of lithium hydroxide. Okay, and that way I know that the chemical I've switched to, which is why I switched colors of pen, is the sulfuric acid. All right, now we are looking for a concentration. So concentration is going to be moles per liter. So that tells me I have moles. I just need to divide by liters. But if you want to use the slider for help, I'm going to make sure that the right-hand side is on concentration. And it tells me down here, I'm going to multiply by 1 on top and the volume in liters on bottom. Okay, so if you want to do like, Jay, were you the one who said put it in liters to begin with? Yeah, so you could just change it to the 0.019, or you could use the 1,000 to change. So let's take a look at that. The answer from step 2 becomes the beginning of step 3. Am I still on the page? I have 1 on top. And then on the bottom, I'm going to have my volume. So if I left it in milliliters, I could have 19.13 milliliters. But then I would have to have my conversion with 1,000 milliliters over 1 liter. So when you're finding the concentration, this is the one time where we don't have units because we're looking for something that is a combination of two. So we don't have to have the unit there because we don't want to cancel out things. All right, so the moles stay, the milliliters cancel, the liters stay. Let's see. I get 0.07035. And we had 4 sig figs, 4 sig figs, and 4 sig figs. So I'm going to make sure I have 4 sig figs at the end. I want my answer to have a number, units. So the units I didn't cross out were moles per liter, and a chemical. And then I'm going to be nice to Dr. Nat and put a little box around it to kind of quickly give you my good grade. Yeah. If you want to have a big M here instead of moles per liter, that's fine. I know the difference between them. Okay, now let's take a look at a couple other things that may show up. Okay, I was hoping we would be able to go over types of equations today, but we're not going to have a chance to. So we're still just dealing with double displacement. So let's say this on the screen. We have sodium carbonate, aqueous, and silver nitrate, aqueous. These are both ionic compounds, so that tells us this is double displacement. What is going to be, or what are going to be the products of this? What do we do? This one isn't on the paper.
So
We need to swap partners, right? And we can't put the two positives together. They'll repel each other, so I have to put the positive with the negative. Okay, so one of them is going to be, run out of room here, NaNO3, but I need to pay attention to charges. So what's the charge on a sodium? +1. What's the charge on a nitrate? -1. So that's one we memorized. And so those two balance each other out. They cancel. They're fine. Okay. Now I'm going to put the inside ones together. I'm going to write it below so I can stay on the screen. So I'm going to put the metal first. That's what allows us to do the outsides and the insides, is that it keeps the metal, it keeps you from choosing the two metals to put together. All right, what's the charge on the silver? Now, this is one that is always the same, but if you don't remember, we can go back to silver nitrate. So nitrate was -1. What does the silver have? +1. And what's the charge on the carbon? -2. So if we look at this one, sodium was +1. So this one has to be -2 since there's 2 sodium. It's also one we were supposed to memorize, but you have clues you can look for. All right, so is this charge balanced? No. So what do I need to do? We need 2 of silvers. Now it's charge balance. Okay, so on your quiz, you'll have to come up with a product. I'm not going to make you balance this. Okay, I'll have a different question where there'll be a different equation that you have to balance, but you're not going to have to do 2 concepts at the same time, and that's fine. Just for the sake of saving some time, I am going to use this for the next question I'm going to ask you. Suppose I needed to put this into the net ionic form. So this is called the molecular ionic, and I hate that name because they're not molecules. The net ionic form only shows me the things that are participating in the reaction, which means it ignores things that are always aqueous. Okay, so that means I gotta label my products for you. All right, everything on the reactive side is aqueous. On the product side, these are not, but these are. So that tells me if these are aqueous on the product side, then they're aqueous everywhere. So my spectator ions are aqueous on both sides. And I want to cross them out because they're not doing anything. They're just hanging out in the water, enjoying the lovely currents. All right, so sodium and sodium get crossed out, and nitrate get crossed out. So now I'm ready to go to the net ionic. That's going to be the things that didn't get crossed out. So I have the CO3, but now I've got to put the charge with it. I took away the sodiums and they were +1. So now we have the -2. On this side, it's aqueous. And then I have my silver. What's the charge on the silver? +1. So I have the nitrate there that is -1. That's what tells me it's +1. And then I've crossed out that chemical. It was aqueous. I'm going to go to the other chemical. Ag2CO3 sub. Okay, so the net ionic equation is showing me which ions that were dissolved or aqueous came together to form a solid compound. Okay, I do want to talk a little bit about solubility rules before we get to the quiz. This is in section 4.2. And in section 4.2, they basically give you a table that says, for this ion, it's always soluble. For this ion, it's soluble with this exception. For this ion, it's insoluble with this exception. This is not on the quiz. It'll be on your test, but it's not on the quiz. All right. This flow chart, instead of looking at individual ions, I mean, you are going to look at the individual ions, allows you to look at a compound and go back and forth between the ions to determine if it is soluble or insoluble. So you'll see at the top, if you answer yes to the question, you're going to follow the arrow to the right. If you're going to answer no to the question, you're going to follow the answer to the down. Okay. So the things you need to memorize are the things that are always soluble. The cations are super easy. Group 1. That means lithium is always soluble, sodium is always soluble, potassium is always soluble. That's why they show up so much in these double displacement reactions. And they end up being spectators because they don't precipitate out with anything. Okay. There's one other, and that's our polyatomic cation, ammonia. So if I have lithium carbonate, if I have sodium hydroxide, if I have ammonium sulfide, just knowing what the cation is, no matter what else is attached to it, you know it's soluble. Okay. If it doesn't have one of those, then you can look at the anions. And there are some anions that are going to be always soluble. Now, for cations, group 1 is all +1, and ammonium is +1. So having a low charge is helpful. We're going to find that true with our anions. All of these are -1s, but I don't have a group I can go to. So you just have to memorize these. The two I use most commonly are nitrate and acetate. You will also see perchlorate or chlorate. Depending on what textbook you're looking at, sometimes chlorate is listed and not perchlorate because perchlorate isn't really used commonly because it's pretty dangerous. Other textbooks go the other way and they say perchlorate is more soluble, so let's list that one, but not the chlorate. But they're both pretty much always soluble. The last one I avoid, but I am going to put it on this list for completion, and that is hydrogen carbonate. Now, the reason why I avoid using that one is it's a little bit tricky. If I take away the hydrogen, the carbonate ion is usually insoluble. That's usually going to form a solid. With the hydrogen there, it always is. So you kind of have opposites for something that looks very, very similar. So I'm going to avoid doing that. I'm honestly not trying to trick you. All right. If none of these ions are in here, then we start looking for things that are usually salt. So sulfate, our old friend there, that's usually soluble, but there are some exceptions. So when I go to the side, it doesn't just say soluble. I'm going to have to ask myself a few things about the cat. The other one, or the other group, and so this is a group, I'm going to use X. That X stands for any halide. The halides are the ions in the halogen group, or group 17. Okay, so X could be fluorine, could be bromine, could be chlorine, could be iodine. All right, so let's look at a couple of examples. If I have iron 3 nitrate, the first thing I'm going to do is say, what's the cation? Is the cation in group 1? Iron in group 1? No. And it's not ammonium, so I don't know yet. So the answer is no, so I'm going to go down. Then I'm going to look at the anion. Is that anion always soluble? Yeah. So this compound will be soluble. It is soluble entirely because of the nitrate. Okay. Now, if I have iron chloride, iron prechloride, I'm going to run into a little bit of trouble because I'm going to get here and I'm going to answer no. And then I'm going to come here and it says it's usually soluble. So if I have to make a guess, if I can't remember this stuff over here, if I have to make a guess, I'm going to say soluble. But there are some exceptions. So in addition to these always solubles, I want you to know silver and lead are the opposite. They are always insoluble unless they are paired with one of these guys. Okay. No matter what I pair lead with, unless it is an always soluble one, it's going to be a solid. Okay, so I'm going to go over and I'm going to say iron chloride. That is not one of those two. So I'm going to go down. And then it says it's the anion, the negative one, a heavy halide. So my halides are group 17. The heavy ones are not fluorines. That means chloride, bromide, or iodine. All right, so is my anion in this compound here, does it fit into this category? Yeah. So then I'm going to go over here, and then I got a couple other things I got to ask about. Is my cation, is iron the same thing as copper or mercury? No. So then I go down, and that is also soluble. Okay, so we'll finish looking at the chart on Monday, but that's kind of the basic flow of it. If this is confusing to you, look at the tables that are in chapter 4, section 2. It's organized a little bit differently, and that might make more sense.